So here we consider a transfer function like this. So you can see it is an all pole transfer function. All the poles are there. I don't have any zero in my function. It is an all pole transfer function. And I take the denominator and write it in the form of an equation in the decreasing power of s. So bn s power n plus bn minus 1 s power n minus 1 plus etc. up to 1. So I write it in the polynomial in the denominator. Okay, I write the denominator in the form of a polynomial. And you know, Bn is the simply a sum of all time constant. B1 is the sum of all product and sum. So Bn is going to be the product of all, the first coefficient Bn is going to be the product of all time constants. And you know, the next one, B1 is going to be the sum of all time constants. So near the three, see, when you have a frequency response graph, when you have more number of poles, so the first order term only is going to dominate. So as you have more and more number of terms, the denominator, the study says that only the first order term is going to dominate. Only the first order term is going to dominate. Okay. So we take the first order term alone, a naught by b1 into s plus 1. And I can write this equation as this is going to be the B1, as we said, it is a sum of all the time constants, right? So I'm taking sum of all time constants, summation I is equal to 1 to n tau I into s plus 1. See, B1 is going to be the sum of all time constants and Bn is going to be the product. We don't consider Bn, we consider only B1 because we say that the first order pole is going to dominate. So even though you have so many terms, it is the first order pole or s power 1. That term alone is going to dominate. So I take only that term. So I write it as a naught by b1 s plus 1. And b1, you know, it is sum of all time constants. So b1 is going to be summation I is equal to 1 to n tau I into s plus 1. So approximately the upper cutoff frequency is going to be 1 by b1, or it is going to be 1 by summation I is equal to 1 to n into tau I. So as we've seen in this equation, it is directly, we say it is dependent on the first order pole. And whatever you calculate, the estimate, actual the upper cutoff frequency value will be different. So what you find here is going to be the estimate of omega h. So omega h is going to be the upper cutoff frequency. So now having understood what is the first order expression. Now we go to second order. Second order, you see we have the expression having power 2. So minus tau 1 tau 2 omega h square estimate plus j into tau 1 plus tau 2 omega h into estimate plus 1. So this is the equation of the second order denominator. So now you can see the magnitude of second order term is unity. As a consequence, you can have these two terms have magnitudes greater than unity. So two time constants are there, tau 1 and tau 2, because it is a second order system. Okay. So the worst case occurs, so two time constants are there, and they say that the product of these terms must be small when compared to the magnitude of the first term. Okay, and two time constants are there. They say the worst case when two time constants are equal, and even then the second order term is only 1/4 as large as the first order term. So they are comparing the magnitude of different terms. So here in first term you have product, in second term you have sum, third term is 1. So when you compare first and second term, if both the time constants are same, the first term will be tau square, which is very much larger than 2 tau. That's what they are saying. So when time constants are equal, the first term is very, very large when compared to the second term. So the same way, what we can do, we can increase the number of terms. So initially we have considered first order. Now we have considered second order. Then we can go for third order. So as we grow for more number of dominant poles, the complexity will also be